Final Mini-Project Presentation ในรายวิชา EL 253 Digital System Fundamental และ EL 255 Digital System Fundamental Laboratory ในเรื่อง Transmission of Digital Audio Using Visible Light Communication Technology การส่งผ่านข้อมูลเสียงดิจิทัลโดยเทคโนโลยีการสื่อสารด้วยแสงที่มองเห็นได้วัตถุประสงค์ของโครงการนี้คือเพื่อศึกษาและเข้าใจถึงธรรมชาติความเปลี่ยนแปลงทั้งเชิงกลและทางไฟฟ้าของสัญญาณในประเภทและสถานะต่างๆเพื่อเป็นจุดเริ่มต้นในการศึกษาเชิงลึกในด้านการประมวลผลสัญญาณประเภทต่างๆและเพื่อนำความรู้จากบทเรียนมาประยุกต์ใช้ในเรื่องที่สนใจขอบเขตการศึกษาของโปรเจกต์นี้จะศึกษาทฤษฎีเบื้องต้นเกี่ยวกับเทคโนโลยีการสื่อสารด้วยแสงที่มองเห็นได้การออกแบบวงจรตัวส่งสัญญาณและตัวรับสัญญาณการอธิบายการทำงานของวงจรการทดลองผลการทดลองและสรุปผลรวมถึงแนวทางการต่อยอดค่ะอันดับแรกนะคะก็จะเป็นวงจร Audio VLC Transmitter Circuit Diagram นะคะจะเป็นอยู่ในรูปของตัวนี้นะคะโดยที่ component ที่เราใช้ก็จะมี resistor 22K resistor 1K 3R9 หรือว่าเป็น resistor ตัว 2K มาต่อขนานกันนะคะจำนวน2ตัวแล้วก็มี capacitor 82 microfarad มี capacitor 100 nanofarad มี transistor 2N 2222A มี LM358 นะคะสำหรับการ calculation สำหรับ audio VLC transmitter circuit the maximum input signal is 1 VPP an audio signal riding on a 0.5 VDC bias the bias voltage or V bias is needed as the currents flowing in LEDs are unipolar as such the bias voltage is 1 to 24th of the 12 VDC power supply and is set by means of the voltage formed by R1 and R2. A possible solution would be R1 equal to 23K, R2 around 1K. And as the 23K resistor is not available, R1 will be set to 22K. We have to keep in mind that to set a lower value such that V bias is slightly higher than 0.5 volt. If it was somewhat below 0.5 volt, the audio signal, or VI, would cliff off below its maximum negative value. The appropriate range of a resistor value should be large enough to limit the power dissipation and small enough in comparison with the internal input resistance of the op-amp. Plus that if the resistor value is not negligible compared to the input resistance of the op-amp can no longer be assumed as ideal, resulting in faulty operations for op-amps such as the LM358, which are built with the BJTs. The internal resistance are tens of mega ohms, and the resistor should be limited to the range of 1K to 680K for op-amp built with FETs, which have their ohms input resistance. Resistances can be several mega ohms, which in practice are the highest resistance available. The purpose of C1 is to prevent the audio source VI from short-circuiting R1, effectively removing V bias. Capacitor C1 block DC voltages and low frequency AC voltage. Since an audio signal needs to pass the cutoff frequency FC to the high-pass filter HPF formed by C1 in a series with a parallel circuit of R1 and R2 is set to 2 Hz, which is an order of magnitude below the minimum of 20 Hz of the audio signal range of the headphone. In parallel circuit, the result resistance is always lower than the lowest resistor value. Since 1K is significantly lower than 22K, it may be assumed that the result of the resistance R1 to equal 1K. The value of C1 hence can be calculated as the formula of FC equal 1 by 2 pi times R1 and 2 times C1. And we can calculate C1 by 1 divided by 2 pi R1, 1 to FC, equals to 1 by 2 pi times 10 cubed, and then times 2, which around 80 microfarad. And the higher available value of the capacitor is 82 microfarad. Since the power of the LED spotlight is 6 watt, and its supply voltage is 12 volt unknown, the maximum LED current, ILED max, can calculate as ILED max equal P which is the power of the LED, which is 6, divided by V LED, which is 12. The I LED max will equal to 0.5 amp. And to find the R3, which is the resistor right here, we can calculate by V bias divided by I LED max, which is 0.5 amp, and our V bias is 0.5 divided by 0.5, also divided by 2. Our R3 will be 2 ohms. And next is the audio VLC receiver circuit. This one we also use the resistor 1K, R1, R3, 4, and 5 they are all the same, which is 1K. R2 and R6 are 100K, and C1 is 22 microfarad, and C2 is 18 farad, and we probably just going to use 22 nanofarad because we couldn't find the 18 nano. And the C3 of 100 nano, and we're going to use the photodiode, the SF806K, and we're going to use LM358, which is located right here. We use 2 of them in this circuit. And to calculate the audio VLC receiver circuit op-amp, we call them UI. And they're going to have like UIA and UIB, for example. R1, R2, and R3 form a current amplifier, which a UIB, and R6 form a transimpedance amplifier, which respective amplification factors are AC equal R1 plus R2 divided by R3, and ATI equal R5 plus R6. Since the capture range is unknown, a wide variable amplifications range should be implemented toward this end. To potentiometer the adjustable resistor over here, R2 and R6 of 100K are used to determine the required amplification factor. R2 and R3 are added to prevent a series signal at the output of the currents and transimpedance amplifier when the value of R2 and R6 are adjusted to 0 respectively. To remove background noise from sunlight and regular LED lamps, which both can be regarded as a DC signals, a high-pass filter needs to be included between the currents and transimpedance amplifier. This high-pass filter is created by R4 and C1. Its characteristic is the same as the high-pass filter in the transmitter circuit, namely the one formed by C1 in the series with the parallel circuit of R1 and R2. The difference is that the high-pass filter at the transmitter filter a voltage, hence the capacitance and resulting resistance is placed in the series. The high-pass filter at the receiver filter a current. The high-pass filter at the receiver filter a current. Hence, R4 and C1 are placed in the parallel, and we have to keep in mind that C1 is connected to the inverting input of U1B, which is right here, which is a virtual earth. Capacitor C2 is added to prevent the oscillations due to instability. Its value is calculated by the means of the formula. C2 is equal to square root Cin divided by 2 pi times R5 plus R6 and times GBW. In the given equations above, the capacitor C is the capacitance at the non-inverting input of UIB, which include internal capacitance of the op-amp, as well as the capacitance of the photodiodes SFH206K. The capacitance of the photodiodes is specified in the datasheet of the SFH206K and is equal to 72 picofarad for FET of amp The value which have a lower internal capacitance usually are provided in the datasheets as well. For BJT op-amp which have a lower internal capacitance, the value of the internal capacitance are not specified. In case the value of the internal capacitance of the op-amp are not available in its datasheets, it is prudent to equal to C ion to twice the value of the photodiode's capacitance. GVW stand for giant bandwidth product and is provided in the datasheet of the op-amp as well. For the LM358 is a value equal to 0.7 megahertz. For resistance R5 plus R6, the smallest possible value in other words, i.e. will be 1K is taken into the account form equations that will be explained in the following presentations. And C2 can be calculated as C2 equals square root 2 times 72 times 10 to the power negative 12 divided by 2 pi times 10 cubed and then times 7 times 10 to the power 5, and it will be equal to 18 nanofarad. And for the equation in detail, that will be in the report, which I will attach with this video in the Microsoft team as well. Capacitor C1 is so-called decrypting capacitor, which is act as an energy reservoir for the op-amp's power supply. It prevents rapid change of the voltage power. It prevents the rapid change of the voltage at power supply pin of the integrated circuit, the IC. It needs to be placed as close as possible to the power supply pin 8. A detailed explanation of the decoupling capacitor will be explained in the datasheet of the product, which also attached with the project report as well. And next we're going to see the video of how this project worked. So I basically built the receiver and transmitter, and I try to open everything up to see if our transmitter worked, and it's worked. The light is it's lit up and it's kind of work. But we don't know if it's actually transmit any information with it or not. So we need a receiver to check if the audio signal actually travel with the light. So we're going to check it out. I think what I'm about to do is I'm checking the audio input, which is the port in my computer. And if everything working, we're going to hear the Aerosmith track. I don't want to miss a thing, but let's see if the receiver actually work. And it's not working. We actually cannot hear anything. Everything is silence, because I don't know if the problem is because of the transmitter or the receiver. That could be both wrong, but yeah, nothing happened. So this is the overall look of the setup of the prototype. This one is a transmitter circuit and this one is a receiver circuit. And I use switching power supply to power up this transmitter circuit, but another power supply is kind of broken, so I use the Arduino to give the 5-volt power to the circuit instead. And this is the end of the presentation. Thank you so much.